Alrighty, folks. So today we're going to be talking about section 4.2, which is all about a collection of rules for probability. I think the section itself is titled... I really shouldn't try to talk when I'm writing the word probability because for some reason I can never remember that second beat. But the section is titled, I think, addition rules. But there's really a lot more rules included in this section. For example, first rule that we want to talk about is, remember we introduced this notation here, right? This P of E, it looks like a function if you've taken pre-calculus or something like that. And that means the probability of the event E happening, right? It's a lot to pack into just a few symbols. But what this means is the probability of an event happening, right? And the thing with probabilities is they're always positive. There's no such thing as a negative probability. So the probability of an event happening is always greater than or equal to 0, right? If it's not going to happen at all, it's just 0. It never becomes negative, right? And probabilities cap out at 1, right? If the probability of something is equal to 1, it's guaranteed to happen. And you can't actually be more probable than guaranteed. So all probabilities of any event whatsoever, no matter what, are between 0 and 1. And in fact, specifically, the probability of, if the probability of something is equal to 1, then that event is actually the entire sample space, right? So the probability of the entire sample space happening is 1, right? Because the only thing that's guaranteed to happen is that something will happen. And if your event contains all of the possible outcomes that might ever happen, that event's just called the sample space. Right? And our third rule sneakily introduces some new notation, right? That no sign in math refers to the empty set, right? So it's basically a collection of things that has nothing in it. So this is saying the probability of the event where absolutely nothing happens, where there is no outcome, is 0. Right? So the probability of nothing happening is 0. Keep in mind this is in the context of running an experiment that, by its definition, has random outcomes, right? An experiment is something you can do that will have an outcome. So the idea of nothing happening, either we're playing semantics and nothing is secretly an outcome, or it means that the experiment didn't run. So the probability of the empty set here is nothing. And our next rule also introduces some new notation, though they're a little bit less sneaky about it this time. And that is that the probability of the event E, when you add it to the probability of the complement of E, right? This C here stands for complement. When you add those together, you get 1. Because the definition of the complement of E is everything in the sample space that's not in E, right? So if you think about it, this is really just saying either something will happen or that particular something won't happen, right? And if you break it down to that, yeah, that's guaranteed to be true. Either something happens or that thing doesn't happen. There's no in-between in that statement. That's guaranteed to be true. That's 100% going to happen. And that's what that 1 stands for, right? You can also think of this 1 as 100%. So those are some of the basic rules. The addition rule that the chapter is named after is that the probability that E or F happens is equal to the probability that E happens plus the probability that F happens minus the probability of E and F happening at the same time, right? And the easiest way that I've seen to show that is by Venn diagrams, right? So if this is E and this is F, right? If you want, so this is E, right? This is the probability of E. This represents the probability of F. And if what you want to know is this, then we'll notice that when we add the green to the blue, let's see, do I have another color? Well, purple probably won't show up. Let's do brown. Let's see if brown shows up, right? This bit here in the center, that's counted twice, right? If you're adding the green to the blue, well, that piece in the center with the squiggly stuff, that is counted once in the green and once in the blue, right? So to get the orange lines, or red lines, then we can add all the green area to all the blue area, but then we have to get rid of one copy of the thing that we added twice, right? That's why we get this subtraction going on, is because adding green to the blue adds that particular space twice. So if you have two of something and you want to only have one of that something, you throw away one of the something, or maybe give it to somebody else. In this case, we're wasteful and we have to throw it away, right? So one thing they note in a sort of side thing here is they bring up the definition mutually exclusive, right? And this means two events that can't happen at the same time. Right? I can't be under 12 and over 40 at the same time. That's impossible, right? So if you're looking at the event that the person that you're interviewing is under 12 and the event that the person that you're interviewing is over 40, well, those are two mutually exclusive events, right? And they get brought up at this point because the probability of E and F equaling 0 is another way to define that, right? So it means that it's impossible for those two events to happen at the same time, right? The probability of something equaling 0 is saying that it's impossible, right? Let's see. So let's see. Last section, we had a problem set up where we had, oh man, what was it? 15 black socks, 6 white socks, 3 blue socks, and 2 red socks. And we picked a white sock first, right? And before we just did a simple problem of what's the probability that we get a matching pair, right? So now we're going to suppose that we are okay with either wearing a matching pair of socks or going with black and white color scheme. Right? So then we might ask, what's the probability that we are okay with our random draw. So, in this case, right, according to our formula, right, this is really saying what's the probability that we draw a white sock or draw a black sock. Right, if we interpret this sentence here, that's what we're okay with. Either drawing a second white sock or the black-white color scheme means it's okay to draw a black sock. Right, so our addition rule says that this is the probability of drawing a white sock plus the probability of drawing a black sock minus the probability of drawing a white sock and a black sock. Right? But really, if we think about it, we didn't need to use the full addition rule because these two events are mutually exclusive. We're drawing one sock. Our socks are not multicolored. We are not that cool. So it's impossible to draw, if we are drawing one sock, to draw both a white and a black sock. So our events are mutually exclusive. So the probability of drawing a white sock and a black sock is 0. Right, so we just need to know the probability of a white sock, which we figured out was 1/5 last time, plus, right, so now we're looking at the probability of drawing a black sock, right, and this is its own individual probability and doesn't depend on anything else. So we're just looking at our situation up here, right? We already determined last time that there were 25 socks to choose from. And if we look at our description, 15 of them are black socks, right? And the fact that we picked a white sock first doesn't change that because drawing a white sock doesn't change the number of black socks there are. Right, so we can get a common denominator, add them together, and figure out that so long as we're willing to go with a white and black color scheme instead of just pure white socks, then our odds of being okay with our draw have bumped up to 4/5. So we can also do some interesting things with this. Yeah. So, yeah. So also, if we remember from last time, we had that big chart that I'm going to recreate in a slightly different way, right? Remember, we had the low, medium, high, and then we had a whole bunch of nonsense. But I'm going to try and rewrite it here in a slightly different form. Right, so these are all the ones that came from L. And then all the ones that come from high. Okay, so these are the 27 results that we got last time, right? And so maybe we want to find the probability that we rolled either exactly one high or exactly two lows. Right. So this is an either or problem, so it tells us we're going to be using the addition rule. So we either want one H or we want two L's. Right? So this is going to be the probability of getting one H plus the probability of getting two L's minus the probability of getting one H and two L's. Right? So all of these, we have the same number of outcomes for each of these given pieces. So that's going to be nice and easy for dealing with these fractions. Right, so now we just gotta count how many of these have exactly one H. So again, because there's enough things here that I want some color to go with it. Let's see, this 1, 2, 3. And I just realized I made a typo here. This should be a medium. So this is another one. Right? Exactly one H. We've got 4 more there. And exactly one H. We've got 4 more there. So as it turns out, there are 12 of these possibilities that we've listed out here that have exactly one high roll. Right? And the rest are either low or medium. What they are, we don't know. Right, so if we want to look for two L's, right, so we've got a 2L here, we've got a 2L here, 2L here, and a 2L here. So we've got 4 again. Right, we've got a 2L here, and I think that's it. And we've got a 2L there. Right, so it looks like we only have 6 of those. Right, and one of the things that's nice about doing this way is it's pretty clear which ones have exactly one H and exactly two L's, right? Because we've underlined it twice, right? And if we didn't underline it for one of the other two, then it's not going to be both. So we know that there's that 2 there. Right, so all in all, we put this together. 12 plus 6 is 18, minus 2 is 16. And we get that the probability of either rolling exactly one high roll or exactly 2 low rolls is going to be 16/27. I don't know why precisely we wanted to know that, but apparently we did. And so we can also have some fun with this formula and play around with it. So I'll show you sort of how we can get to there. So we sent a survey to 30 people asking about pets. And it turns out 17 of them said they had dogs. 19 said they had cats, and 3 had neither. There we go. That's how we spell words. Cats, nor dogs. And we want to ask the question, how many had both? Right, so one thing to notice right here is that on the surface, this doesn't look like a probability problem, right? I'm not asking how likely is it for something, but how many, right? So, but if we think about it, right, especially if we think back up to this problem, right, if I'd ask the question, how many different ways are there to roll exactly one high or exactly too low, I would have been looking at exactly this line and just ignoring this thing where it's all the same number over and over again, right? So this is the exact same kind of question. I just don't need to count how big the sample space is, right? At least not right away. Right? So, the other weird thing here, right, is we have the probability rule that says dog or cat equals the probability, or maybe we just say number here. Number of cat or dog is equal to the number with a cat plus the number with a dog minus the number of both. Right, so cat and dog. Right? And sort of I've given away the trick there is that we're actually asking the question about this one. Right? In both of our other problems, we knew the answer to the both question. Right? In the first case, it was 0. In the second case, we had to figure it out. But in both those cases, we actually knew that one. Right? But in this one, we don't. So hopefully we'll know something else here. Right? Because we definitely know the number with cats. Right? That was 19. And we definitely know the number with dogs. That was 17. This is the number we're asking about. Right? So in other words, both. So maybe we can figure out what this guy is. Right? And so this is where that idea of, man, I blanked on complement. There we go. That's the C word that I was looking for. This is where we can use that idea of complement, right? Because what were we told about? We were told that 3 had neither cat nor dog, right? So if E is equal to cat or dog, then E complement is going to be neither cat nor dog. Right? If the only question is, do you have a cat or a dog, and you say no, that means that you don't have either of them. Right? So the complement of E is, or the complement of this event that we want to know about is the thing that we actually know about. Right? So if they're complements, that means that between the two of them, right, they make up the whole space. Right? So the number who have neither cat nor dog is 3. The total number is 30. So the people who have either a cat or a dog is 27. Right? So that's where that idea of complement comes in. Right? Remember, this is not a probability. This is a counting thing. Right? But remember, the probability of E plus the probability of E complement equaling 1 means that between E and E complement, you have everything. Right? So that's why this 30 comes into play. So we have a 27 here. We figure out that 27 equals 36 minus the number that have both. And we can do a little bit of algebra to figure out that the number who have both is 9. Right? So in that case, for most of the problems in this section, we know the and we're trying to figure out the or, but it turns out that you can use either of them to figure out the other, right? As long as you know one, you can figure out the other. Alrighty. So that's the basic kind of problems that we have in this section. This last one we did here is about as complicated as they get. And so next time we're going to throw multiplication into it, right? So we're going to get a couple more rules. We're going to get a couple more definitions. And we'll round out our talk about probability. So I will see folks then.